The next speaker is Andy Davis with USB Undermining Security Barriers.
Thank you. Morning, everyone. My name's Andy Davis. I'm Research Director at NGS Secure. And today I'm going to talk about different ways of identifying vulnerabilities in USB stacks and USB devices. So quick run through of the agenda. First of all, so that I cover off all the terminology associated with USB and make sure everybody's on the same page with how USB works. We're going to go through a quick USB primer, talk about some of the previous work that's been done in this area, as a number of people have approached USB security from different ways over the years. We're then going to look at different vulnerability classes associated with USB bugs, and then talk about specifically some of the research that I've been involved in, the development of a bespoke USB fuzzer, implementing a more powerful fuzzer using commercial test equipment, and bringing it all together, showing you a demo of what the fuzzer can do and the kind of bugs that it can uncover. After that, we'll bring it all together and talk about the actual real-world security impact of some of these bugs, because a lot of people will look at USB-type vulnerabilities and say, yeah, but what does that really mean to me, mean to my business? And then finally, we'll wrap up with a conclusion. So, USB. I'm sure I don't need to tell anyone in the room that it's absolutely everywhere these days. PCs to PlayStations, TVs to toasters. Yes, you can get USB toasters. In one of our offices in the UK, we've got a USB-enabled microwave oven. So the fact that USB as a technology is so widespread means that any potential vulnerabilities in the way that USB processes data, in the way that it works, can have a huge impact across lots of different technologies. So as I said, we're going to start with a quick USB primer, just to explain how the technology works and what it's all about. So USB was designed a few years ago. I'm sure many of you, if you remember back to the days of PCs where if you wanted to connect peripherals, you had to install ISA cards and PCI cards and setting interrupts and all kinds of stuff, and it was really, really a right pain to get anything to work together. So a bunch of different companies got together and thought, wouldn't it be great to have this universal approach to connecting peripherals to PCs, and that's how USB was born. There are 3 speeds of data transfer. Now, this is associated with USB 2. The majority of the stuff that I'm going to talk about in this talk is USB version 2.0, which is the most popular around today. There are other versions, there are older versions, and of course the newer version 3.0, which I'll touch on when I'm talking about comparisons with the different technologies. But the majority of the stuff will be focused on USB 2.0. So you've got these, initially there were 2 speeds, low and full. Wasn't particularly forward-thinking of them to call it full speed, because then of course FireWire came along and they needed an even higher speed. So high speed is significantly faster than full speed. USB as a architecture is a tiered star topology. So basically you've got a single host controller, which in most cases is a PC, and you can have up to 127 slave devices. Now the restriction of the 127 is purely down to the amount of bits that can be allocated to an address in one of the structures that are used. So you can plug devices into a hub, and you can plug hubs into hubs, but the maximum number of tiers you can have of hubs connected to other hubs is 6. Host is always the master. So in a traditional scenario where you've got a PC connected to a whole bunch of USB devices, it's the host, your PC, that initiates the communications with the devices. You can't have devices talking to devices or devices saying, I want to do something, I want the host to do something for me. There is one exception to that. There's another USB protocol called On The Go, which I'm sure some of you will have heard of. And the concept of On The Go is to allow a bit more functionality within devices, to allow devices to talk to others. So let's say you've got a USB camera and you want to print out some photos that you've taken on that camera. Instead of having to download the photos onto your PC, then print from your PC, you could just connect your On The Go enabled camera directly to your On The Go enabled printer and just print directly from the camera. But that's a separate protocol and not something that I'm going to talk about in any detail today. So USB is a bus. So when the host is communicating, all the devices on that bus can see the data, but they only process the data associated with the address that's been allocated for that device. So once a device has been enumerated and it's up and running on the bus, it's been allocated an address, and data associated with that address gets processed by that device. Each USB device has got a number of so-called endpoints, and each of these endpoints is a source or sink of data. So you can have up to 16 out and 16 in, out being from the host to the device and in from the device to the host. And there's a special endpoint called endpoint 0, which is used for specifically controlling the device rather than exchanging data in its normal usage. A pipe is logical connection between host and a particular endpoint. There's only a few more of these type of slides, I promise. We need to get this stuff out of the way first. Configurations, interfaces, and endpoints. Okay, so the device has got a number of descriptors, and descriptors are going to be very important when we come to the fuzzing, as you'll see later. So they've got lots and lots of information about the capabilities of a USB device. And you have what's called a configuration descriptor set. So let's say you've got a device that can perform different functions. Sometimes you have USB devices that, rather than just being, say, a mass storage device or being a camera, they've got multiple functions in them. So they might have a hub as well as a mass storage device. And you'll have different configurations associated with those. Maybe you've got different power options, different power requirements for the different areas of functionality within the USB device. So each of these configuration descriptor sets has got different amounts of information about the capabilities of a USB device. Interfaces. You can have multiple interfaces. Again, this is normally to do with the different areas of functionality within a USB device. And that, yeah, they represent these different functional units. We've already talked about endpoints. Okay, so what actually happens when you plug a USB device into a host? I'm sure many of you will have an idea of what you see, certainly from a Windows perspective, when you plug in let's say a USB mass storage device. You'll see a little pop-up saying, this is the vendor name and this is the type of device it is. But what's actually going on under the hood from the moment that you plug it in until the moment that you can use the device? Well, the first thing that happens is within the USB interface, you've got a power line and a ground line, and then you've got two data lines, one called D plus and D minus. And when you plug the device in, at an electronics level, there is what's called a pull-up resistor, which connects onto the data line, and it will indicate to the host that a physical device has been connected to the USB bus. So the host says, okay, right, we've got some technology that's been connected into us. I'd like to start grabbing some of these descriptors because I want to find out what this device does and what I can use it for. So it requests the device descriptor and asks for what the maximum packet size is that can be used within USB, and using address 0, special address that happens at setup time. It then resets the device and so that it's in a known state, and allocates an address somewhere between 1 and 127 for the device so that it can be used. It then asks again for the device descriptor. The first time was just to get the max packet size so it could work out how it could communicate with it. This time it's actually asking for the basic capabilities of the device. And this is all happening within the host controller interface driver. So that's the driver that comes bundled within your OS that understands what USB devices are and how to initially communicate with them. Once that's happened, information starts communicating with the USB bus driver. And what that says is, okay, I want a bit more detail about this device. I know within the device descriptor it's specified things like the vendor and the type of product, which we'll come back to in a minute. But now it's asking for more specific information. So for example, those configuration descriptor sets that I talked about, those all get downloaded. And string descriptors, as I said, when you plug in a device, certainly in Windows, you'll see the little pop-up saying the strings that come out of the string descriptors that say, yeah, this is a mass storage device or whatever. And then one of those configuration sets is chosen by a set configuration command, which is sent to the device. Now, at that point, it's almost ready to go. What it needs to do is, if, for example, it's a pretty standard device that the operating system's likely to understand by default, like a mass storage device or maybe a keyboard or a mouse, that kind of thing, those device drivers come bundled with the operating system. But the way that the operating system knows which one of those drivers to load goes back to the information it got from the device descriptor. There's things called vendor IDs and product IDs, and that information's stored in there. So it basically uses those in a lookup table to work out which device drivers it needs to load so that you can actually start using that device. So I mentioned device descriptor. Here's an example of one. All these descriptors are just data structures that are exchanged at the time when the USB device is plugged in. And the vendor ID and product ID, these numbers here, are what are used to identify which device driver to load in the operating system. Okay, previous work. As I said, a number of people have looked at USB security in the past, and various presentations have been given at BlackHat, DEF CON, all kinds of other conferences. And a number of different approaches have been taken to try and identify flaws within USB driver stacks. And incidentally, the majority of the presentations that I've seen and previous research that's been done has been focused on looking at vulnerabilities within the USB host rather than the USB device. I won't go through each individual person and explain what they did, but the types of approaches kind of fall into a number of camps. There's the virtualization approach, where you place the host that you're trying to fuzz within a virtual environment, and then you're intercepting the USB communication into that virtual environment and then fuzzing it that way. Another approach was to use USB over IP. So fuzzing actually at the IP level. So again, you're kind of like sitting as a proxy in between the USB host and device, but that point is over IP in that instance. And then there's other people who have taken the hardware-based approach, developed some kind of microcontroller-based solution to emulate a USB device, and then because they've got control of that emulated device, they can fuzz all the information within the descriptors from that. The big problem with all of these solutions is they're all very either host or device specific. They're all, the majority of them are focused on specific classes of USB type devices to emulate. So I wanted to come up with some kind of more generic approach to testing this stuff. And black box testing of USB device driver bugs is very, very difficult because let's just say you've got this device with a USB interface in it. And the thing that got me thinking about this is there have been several kind of security tests that we've had in our company where we've had kind of an oddball box that gets delivered and it's got various interfaces, and the client just wants us to tell us how secure it is. And there are a number of ways of doing that. Obviously, if they're going to provide the source code associated with the drivers, you can do some kind of code review on it. But as you all know, code reviews don't find all bugs, certainly within the constraints of commercial code reviews where there's some kind of restraint on the testing time. It's always useful to have a combination of static code analysis and also some kind of runtime analysis. So I wanted to come up with some kind of runtime analysis approach that would apply to any black box that's got a USB interface in it. But yeah, it's difficult when you've got no real view of the firmware. It's hard to debug. How do you know what's going on when it's crashed? Hard to hook into it. And it's very difficult to get a PC to actually pretend to be a USB device because it's so geared up to be a USB host controller. There's some serious driver development required to get it to pretend to be a USB device. So I needed a different approach. Before we go on to what approaches I took, I thought I'd cover some of the different vulnerability classes that I've seen associated with USB bugs. And just to explain, in this slide, the ones that are highlighted in bold relate to bugs that we've found during this research. The other ones are publicly released information that I've had no involvement in. So as you'd expect, bearing in mind that this is standard software, okay, it's drivers. It's not just drivers, there's some userland software bugs that can be triggered via USB as well, but the majority of the stuff is driver code. But as you'd expect, there are some pretty conventional vulnerability classes that can be triggered within the USB environment. So stack overflows, there are a number of string descriptors, string descriptor-based overflows in Linux and Windows XP that have been discovered. And there was one Solaris hub class descriptor that we identified. Integer and heap overflows. I'm sure you are aware of the Sony PS3 hub class based hack and some of the jailbreak type stuff with the Apple iPod. So the Apple iPod one, you can see that's called 0xA1,1. That's kind of referring to the control message, the USB control message. So because we're talking about a USB device here rather than a USB host, we're not fuzzing descriptors. That's a control message sent from the host to the device. Null pointer dereference, that's quite an interesting one. In a lot of cases, in the majority of cases, if you find a null pointer dereference as part of your fuzzing, it's not going to be exploitable. But in the case of the Apple iPhone jailbreak, because there was a clever way of writing to address 0, this could then be exploited. And then there's also logic errors. There's a HID report descriptor bug that we discovered, and I'll be doing a demo of that a bit later on. So, how did I go about it? Well, the first thing I thought is the most mileage that came out of research that I've seen presented in the past has always been where people have developed their own hardware. They've created some kind of microcontroller-based solution whereby they can emulate some kind of a USB device. You've then got full control of what that device does, what it sends to the host, and therefore you've probably got most flexibility to fuzz the device drivers that are at work. It uses the Arduino. I'm sure many of you are aware of the Arduino as a flexible development, kind of fast prototyping solution. And I'd done some work with Arduino in the past, so it seemed like the obvious solution for me. There were some drawbacks. It only emulated USB HID devices. I wasn't going to reinvent the wheel. People had done some work. Which stack do you use? Which USB stack do you use on the Arduino? There's a link to it on the next slide. So basically, the code that has been publicly released to use USB, I used that. I didn't rewrite anything. As I said, I haven't reinvented the wheel. There's interfacing solutions that are out there from a hardware perspective. So I just went ahead and used that. It was more a case of using the information that was out there and applying security principles to it, which is something that I did again later on with kind of commercial test kit. And that's the fundamental issue here. The fact that, yes, there's a lot of technology out there that will enable you to do this kind of stuff, but the people who've developed that technology haven't really thought about using it in a security context, and that's what I did. That's what I did in this instance. It wasn't a very flexible solution using the Arduino. It only really allowed semi-automated fuzzing because some of the stuff that I needed to modify and resend and manipulate was deep within the driver code, so I had to kind of keep recompiling it. But it did find some serious bugs. It found some bugs in Windows 7, Windows XP, and Apple OS X. So it gave me kind of a justification that there was something here. Although people had done, various bits of research on this in the past, they certainly hadn't used that to identify all the kind of main bugs within these major operating systems. So having found those, I thought, well, I'm onto something here, but this technology, the Arduino approach, is not necessarily the way to go if I want a kind of a platform and device independent approach. It wasn't really fast enough to emulate anything other than HID devices. So the driver code associated with the USB HID device, there's a link there to download that. And there's the simple interface that's used to enumerate. So just to explain, if anyone's used to using the Arduino microcontroller, I'm not using a USB shield here. I'm just talking directly to the data pins via that little circuit there. And then the code that's freely available to download will interface with that. And then I applied my kind of fuzzing principles to the code within the driver. So, as I said, it wasn't really a long-term solution, Fuzzbox. It just kind of got me into the frame of mind of what I could do with USB. I needed something more flexible. And after quite a lot of hunting around, I discovered that there's a bit of commercial test kit available that seems to do most of the things that I needed. And it did involve quite a lot of hunting around, because there's a large number of solutions out there to capture USB traffic, all the way from kind of freeware, Linux, USB sniffers, all the way up to really expensive commercial test kit. But there's not actually that many solutions around that will allow you to play back captured USB traffic, and that was the key. That was what I really needed. So I can capture and play back. I can also emulate USB hosts or devices, which again gives me this maximum flexibility. I can do the fuzzing on the devices or on the hosts. It's got an understanding of all the different USB device classes. So if you think of this device as kind of a hardware-based Wireshark for USB, and the device classes being dissectors, like in Wireshark, it's that kind of thing. And it's another thing that was very, very useful to the way I wanted to use this device was it has its own inbuilt scripting language that allows you to generate the USB traffic. So you can either capture a session, plug in a USB device and capture all the traffic between that host and the host and that device and generate a script from that, or you can write a script from scratch using this the scripting language. So pretty flexible and relatively cheap, about $1,200 as a base solution. The only major drawback of this technology is the fact that it doesn't have a software API to control it. There's software that comes with it, a GUI-based kind of front end that allows you to manipulate the device and get it to execute these scripts and things. But certainly at the moment, there's no kind of automated way of controlling that, so I had to get around that. So this is what the GUI looks like. Probably a little bit small for you to see all the detail there. But essentially on the left-hand side here, this is a capture of communication between a USB device and a host on plug-in. And you can drill down to, all the way down to timing information, much more information than I actually needed. But if you select one of these, that's the response from a get device descriptor request, and you can see on the right hand side here that shows the device descriptor that's being sent back by the device, and then down at the bottom it shows you the actual individual bytes associated with that descriptor. So I mean for me, certainly at the beginning it was quite a useful learning experience trying to understand all the information within these different descriptors. And this product kind of like helped me pull all that information out rather than just wading through all the different standards documents and trying to interpret what all those bytes represent. I mentioned the generator script. This is an example of a generator script that was created as a result of that capture that you saw in the previous slide. It's all pretty nicely laid out. It's quite straightforward and easy to use. There's lots of comments that get automatically put in there to explain what the different sections are. And when you create a generator script from a capture, you either decide that you want to emulate the host or emulate the device. And it still includes all the other side of the communications traffic, but just comments it out. That's what you can see in green there. So what can we fuzz? Well, I've talked about the different descriptors. The different descriptors are being processed by different drivers on the host. So you've got HCI drivers, bus drivers, and device drivers for specific USB uses. And once the initial enumeration process has finished and you start using the device, then you get class-specific descriptors that come into force. And you get, so for example, if you're using a mass storage device, there's lots of like SCSI commands and things like that are very class-specific to that type of technology. So there's a huge amount of scope for information that is being parsed by these drivers that can be fuzzed and therefore trigger software bugs. And on the USB device side, you've got the control messages that are being sent by the host to those devices. So why is this different? Well, I've kind of covered a lot of this already, but the previous approaches have been focused on testing or emulating specific devices or hosts. This approach, because it's taking a kind of a proxy-based Wireshark type playback approach, you can use this with any type of USB device or host, even this kind of black box idea that I talked about, where you've got no idea what's going on under the hood. So we don't really care what the host or device is. If we understand the USB protocol and we understand the kind of software flaws that may exist within the driver code, then we can fuzz from a black box perspective. And as I found, it certainly produces some interesting results. So we've gone from demonstrating that there's still vulnerabilities out there in USB using my initial fuzzbox approach, this microcontroller solution, onto identifying this commercial test kit that looks like it will do what we need it to do. Now we need to incorporate it actually into some kind of fuzzing solution rather than just kind of prodding around with manual byte manipulation within those scripts. So I developed a USB fuzzer called Frisbee. As I mentioned, the graphic USB, which is the name of the Win32 GUI that you get with the product, doesn't have any API for controlling it, so we needed some way of interacting with that to get it to make the modifications that we needed as part of the fuzzing process. What Frisbee does is it actually modifies the graphic USB generator script, which we've generated from our initial capture. So these generator scripts, they're just pure text files, so dead easy to manipulate. And then what happens is when you load them into the GUI application, it compiles them and then uploads them via a control USB connection up to the device where it's executed. So although it's not a particularly elegant solution, Frisbee uses the send keys Python library just to inject Windows events into that GUI. Only a small amount of interaction is actually required with that GUI because when you kick it off, you can use the name of the script that you want to use as a parameter for that, and then all you need to do is hit F5 to compile it and F7 to execute it. So small amount of interaction, and using the send keys library, we can do that. And yes, it's not the ideal solution because it looks a bit clunky. You know, we're interacting directly with the GUI, and it's quite slow. So, for example, you can't fuzz more than one test case every 6 seconds. I discovered that if you try fuzzing any faster than 6 seconds, which I could do with my Arduino, the USB host controller code in most cases just can't keep up because the host controller is expecting a human being to be plugging in a USB device, and then it sits there and goes through its enumeration phase. And because it's expecting it to be in kind of human time rather than computer time, if you try and speed that process up, the code hasn't been written to cater for that. So although this is relatively slow, you wouldn't benefit wouldn't benefit from it if we could make it faster. As far as instrumentation goes, to identify when the host has encountered some kind of bug, I'm just using an Ethernet connection to the device. I'm just pinging the device. Because in most cases, because it's driver code that's crashing, you'll either get a blue screen or you'll get a kernel panic and the box will reboot. So pretty simple solution, but at least you can see when that has been triggered, and then you can go back in and use the graphic USB GUI to investigate manually after you've identified which byte it is that's triggered the bug. Demo. I'm taking the cheats approach, and I'm going to show you a video. Okay, so I mentioned earlier that we discovered a bug within the Windows 7 USB HID driver. There are actually 3 different bugs that we found within this particular area. So this is a demo of one of those. And as I'm sure you can appreciate, watching a fuzzer running isn't the most exciting thing at the best of times, so please bear that in mind. Okay, so just to explain what we've got here, this window here is where I'm executing Frisbee, which is a command line based Python script that's got the understanding of the different device descriptors and understanding of where we can fuzz and what the different fuzz test cases are. That's then interacting with graphic USB. This is the graphical front end to the device. And so it's injecting using send keys into that, loading up the different scripts once they've been modified by Frisbee. And then down here, we've got WinDBG. So the target machine that's running Windows 7 that's being fuzzed is connected via a separate USB connection to WinDBG on this box so that we can do remote kernel debugging. So it's running some different test cases. You can see over here, graphic USB is generating the traffic associated with each of those fuzz test cases. Oh, and there we go. A bug check has occurred. So WinDBG has kicked in because if WinDBG wasn't connected, you'd just get a blue screen and the box would reboot. But we're connected with WinDBG. It says that it's identified the vulnerability in hidpars.sys. And using bang exploitable, looks like it's probably exploitable. And the other, I said that there were 3 of these. 2 of the 3, bang exploitable says it's probably exploitable. The other one is not quite so sure. We're still investigating the full exploitability of those. And once we work out how to fully exploit them, I'll do a demo at a subsequent event and show you an exploit. Okay, so using this technique and this fuzzer, what have we actually found? Well, quite surprisingly, most operating systems that I pointed this at found some bugs pretty quickly. It's quite difficult to, in all cases, identify how exploitable some of these bugs are, because it's quite difficult to get to the bottom of exactly the root cause of what's going on within the driver. Much harder to debug in kernel land than it is in user land. But as you can see, we found vulnerabilities in Windows 7, Solaris 11 Express, Xbox 360, and Apple OS X. There are others as well that are currently being discussed with the vendors. All of those have been reported. So why are these USB-based vulnerabilities so prevalent? I mean, some of those works that I referenced where people have done research into USB security, go back to you know, 5, 6, 7 years ago. You'd have thought that the vendors would have this cracked by now. But different vendors have got different approaches. Some of them don't seem to view USB vulnerabilities actually as a security issue. So I've anonymized these to protect the vendors, but vendor X, and these are direct quotes, thanks for sending this to us. This is something we'll definitely pass on. However, since this requires physical access, it's not something we'll fix in a security update. Okay, that's one way of looking at it. Yep. Sorry? Yeah, I need to think about lawyers. And also, knowledge of how to emulate USB devices is certainly not widespread. Different vendor. These are both major vendors, by the way. Yeah, we think we fixed the issue, but we need to get you to test it, as we don't have the ability to replicate your attack. So, maybe some of you are thinking, well, okay, yeah, you do need physical access. What's the real security impact here? What could you do? Well, there's a number of different scenarios. When you're talking about USB devices, there's been a huge amount of publicity around jailbreaking of devices like the iPhone. So using this technique, it's quite straightforward to identify bugs within USB devices. If you're looking at the USB host kind of scenario, you've got unlocking a locked workstation, and it doesn't take time. If you've got a working exploit against one of these drivers, it's literally a case of inserting it, and during the enumeration phase, so when it's exchanging all these descriptors, that's where the vulnerability is triggered. And you can do a huge amount in a few seconds. Installing malware on a machine, again in seconds, plug a device in. Exfiltrating sensitive data. But hang on a minute, what about these endpoint protection systems? I'm sure many of you within your organizations have got some kind of endpoint protection solution that stops unauthorized USB devices from being plugged in, and that's going to protect you, isn't it? There's a number of these around. I'm not going to name any specifically that are considered vulnerable. There's lots of different solutions, but they all take a very similar approach. They have some kind of policy based on what you want to allow to be plugged in. You might specify specific vendors of devices. You might say, I only want mass storage devices to be used or not used, or I only want HID devices to be used. And then when you plug in that device, the application identifies what that device is and looks at the policy and decides whether it should be allowed to be used or not. The fundamental problem is that they all work higher up the USB stack than many of the vulnerabilities do. So although they are going to protect you from people who are just trying to plug in a normal device that's not allowed by the policy, it's not going to protect you from vulnerabilities within the underlying host driver stack. So if you've got a vulnerability within the host controller that happens at the moment that you plug a device in, it's going to be game over way before we get to the is this part of my policy decision. So conclusions. There's plenty of USB vulnerabilities out there. I've only really been doing this research since the beginning of the year. So I was quite surprised at the amount of vulnerabilities across different operating systems that we found so quickly. Yes, you need some kind of limited physical access in order to potentially exploit some of these vulnerabilities, certainly to trigger them. USB vulnerabilities certainly constitute a serious security risk. Once you've got to the stage where you've actually got a working exploit, exploiting one of these driver bugs, there's a huge amount of potential damage you could do in a corporate environment. Endpoint protection software, as I've just said, is unlikely to protect you from a lot of these attacks. That's not to say that endpoint protection software is bad. As I said, it's certainly going to protect you from the more kind of standard approach of people just trying to insert devices that are not allowed to or that are not within the policy. But targeted USB driver-based attacks are not going to be prevented by these products. So if you really don't want people exploiting USB, then disable it in the BIOS. And if you're really paranoid, fill the USB sockets with epoxy resin. Take the military approach. Thank you very much.